Hello and welcome to another video. In this one we're talking about LTO or link time optimization. That's it, that's all the video. No. I've been asked a few times like what is LTO? Also what is PGO? But we'll probably cover that in a different video. How does it work and why would you want to do it? And so I'm going to talk about it a little bit briefly. Note that I'm grossly oversimplifying how LTO works, and I'm specifically only talking about C projects in this video. It also applies to other programming languages, compilers, etc. I'm also only talking about GCC here. It works slightly differently in LLVM, but the same idea is there. And so you can kind of apply the concept in other places. But let's talk about C programs and how they tend to get compiled. They tend to get compiled in sort of a multi-phase. I'm going to simplify it down to two different phases, one being the compilation phase and the other being the linking phase. In the compilation phase, a bunch of C files, I have already pre-configured two checkouts of cpython right here to demo this. And I've run configure, I've run make once, so we're going to be a little bit faster than usual. The first phase, the compilation phase, takes our C files and compiles them into object files. So that's what this .o is. We also have, I think this is coverage information, so there's other stuff in here as well, but important are the C and the O files here. This is the source, this is where the textual source is written, and the O is the first compilation phase. It takes just this C file source and all of its includes and compiles it down into this object file. Then the second phase, the linking phase of compilation, will take all of the necessary object files and essentially, when you don't have link time optimization enabled, just stitch them together and produce your output. Obviously, it's not as simple as just stitching them together. There's symbol tail stuff and entry points and all sorts of other things. But you can kind of think of this binary that's produced here, this Python binary, as a just a stitched together bunch of object files. Obviously, it's not, but it's close enough to that. Are there any .so files as well? Yes. Okay. So these .so files, these shared objects, are also similar to that. They're also linked together in the same way, linking a bunch of object files together to produce these shared objects. They're similar to the binary, but instead they're libraries instead, and they go through a similar process here. And just to give you an idea of like how long compilation takes, I'm going to show you the non-link time optimization and then the link time optimization, and then talk about how it works and why it improves speed so much. And in order to do that, I'm going to touch some of the C files. This will cause make to notice them as out of date and then rebuild. And so if I should put time there. Let me do that with time. Time make, just to give you an idea of like how long it's going to take to build the binary where each individual C or each individual object file is built. Obviously not each individual, we're only rebuilding the objects that got touched. So this Unicode writer, Unicode C type, etc. And then, so you can see here, these are the individual C files being built, producing the individual object files. And so we get a bunch of these small compilation jobs and then a link job at the end. So it takes all of these .o files and produces, where's the output file? Oh, I guess in this case, it's producing a C file called freeze module, which probably then gets called, I guess gets called on some things to freeze stuff. So we happen to touch a file that's early enough in the path that it causes a bunch of rebuilds here. But you can see here at the end, it took about 13 seconds to do that build. Obviously, this is an anecdotal result and not, completely representative of how a build would take. You would want to profile this to get a more precise result. But anyway, took about 14 seconds. In the link time optimization version, the same two phases happens. You have that compilation phase and then the linking phase. And spoilers, I did the same thing over here, but I'm not going to make you sit through 4 minutes and 23 seconds of building here. And almost all of that, I guess we can show it. I guess we can show the start of this, which is that those compilation units are just as fast as they were in, or maybe they're a little bit slower because I have to do some additional bookkeeping, but they're just about as fast as the original non-link time optimization build. But you can see here that this the actual linking step here takes way longer, and this is because it's doing link time optimization. Now, what is link time optimization? This allows the compiler and linker compiler, the tool chain, to analyze across compilation units. Usually these .o files are considered compilation units in C, and normal linking doesn't do optimization across them. When you enable link time optimization, it can analyze the program as a whole, find things that might be able to be inlined or optimized out or dead code eliminated or things like that. And so it's going to take a lot longer because it has to analyze a lot more of your code in order to do optimizations there. But a lot of those optimizations result in a much, much faster binary on the other end. And so enabling link time optimization on release binaries is usually a good idea. But anyway, wanted to sort of give you a little mental concept of link time optimization, how it gets used in building C applications, and a demo of it taking for goddamn forever when it's enabled. So it's something that you probably don't want during development. But okay, now it's progressing onwards. But I'm not gonna force you to sit through all 4 minutes of it. Thank you all for watching. If you have additional things you would like me to explain, leave a comment below or reach out to me on the various other platforms. Wow, why am I butchering my outro today? Anyway, have a good one. See ya. Hold on, I clicked the wrong button.